Hello, everyone. Good morning. My name is Kumeresan, and I'm a lecturer in Center for Artificial Intelligence and Robotics, University Technology Malaysia. I hope everyone can hear me. And on this MACE online technical series this morning, I'll be talking about reinforcement learning in robotics applications. So first of all, I would like to say thank you to the organizing team for having me today. So let me begin with concepts of the agent, action, and reward, because these concepts are being used in reinforcement learning. So an agent is an entity or an object that interacts with an environment by performing tasks through actions. In return, the environment generates states to be observed and rewards to be received by the agent. So it has an overall task to perform, and it execute that task by taking actions at regular time steps. So on this slide, I have the red car as my agent, and the task or the overall objective that has to be carried out is to drive to the location of the smiling trophy. However, the agent has to take some actions at several locations along the way. In particular, at location 1, the agent has to decide whether to follow behind the blue car, to knock the blue car, or to overtake the blue car. And each of these actions has its own rewards. For example, if the agent follows behind the car, the agent will obtain a negative reward. So why negative? I hope you can hear me. However, if the agent overtakes the blue car, the agent will receive a positive reward because it can now reach the destination fast. And similarly, at location 2, the agent has to decide or take action whether to turn left or to turn right. All right. So if it turns left, the reward is a negative reward because it will take more time and more fuel consumption to reach the destination. If the agent turns right, they will get a positive reward. And same thing at location 3, it has to take action 3 as well. So if we simply instruct or tell the agent that it has to achieve its objective, that is to reach the destination where the trophy is, so the agent might overtake or might follow behind the blue car. It might turn left, and then from here it might turn right and go in circles until at one point it goes straight to reach the goal, which is not wrong. However, if I tell the agent that not only it has to reach its destination, but it has to maximize the sum of rewards along the way, then the agent will go here, overtake the car, turn right, and turn right again. So hence, it will take the fastest route to reach its destination. So it's critical that we provide instructions to the agent such that not only it has to reach its goal, it also has to maximize the instantaneous rewards that it collects along the way. So these concepts of agent, action, and reward can seemingly be observed in many other applications. And one of the applications would be our good old closed loop control system. So here the controller can be viewed as an agent, and it performs or it takes action by means of the controller output, and the plant and the sensor or the feedback mechanism can be considered as the environment. So once again, if we tell the agent that the overall task is to take action such that the output should be equivalent to the set point, then probably we'll get the blue line, which is not correct, which is okay. But if you want a better performance, you should instruct the agent or the controller to maximize its rewards along the way as well. So if we set the reward to be a positive reward, as long as it does not overshoot, the response does not overshoot, then we'll probably get this red line, which is better in some applications compared to the blue response. And of course, another application would be in robotics. So if we have this 3-joint robotic arm, and the task, the big objective is to pick this trophy, the smiley trophy again. If we do not explicitly say or impose that the robotic arm has to maximize its rewards, then probably the end effector will be turning away from the desired pose, and then only finally it gets to the desired pose to pick the trophy. But if we, on the other hand, if we set a positive reward each time the end effector gets closer and closer to the destination, then we can get a transition of configurations like this. So at state 1, we begin with this, and it goes to state 2, it gets closer because it wants to collect the reward, and then it goes to state 3, it wants to collect another reward, and finally goes to state 4, where it reaches its goal to carry out the tasks. So having that said, well, we are ready to formally define what is reinforcement learning. So formally is an approach for learning decision making and control from experience, right? And the goal is to find a set of actions that maximizes the sum of rewards. So this is a typical reinforcement learning scenario. So like I said, the agent will take action, but the problem is, how do we know these actions are the best? And once we obtain or observe the state and receive the reward from the environment, and how are we supposed to use this information to improve our understanding of the environment and to produce the optimal action such that to maximize our rewards? So that is the reinforcement learning problem. So in a typical or conventional robotic control pipeline, let's say the task here is to pick an object from this pose and then to place it in this pose. Normally what we would do is we would get some observation. These are measurements, right, through our sensors. So you can imagine this is like output given by the camera, images. And from using those images, we want to estimate the states. And then from the state estimation, we would do some modeling and prediction. Typically, we would have some computations of forward kinematics and inverse kinematics here. And then we would do the trajectory planning. And once we have the required joint angles, we would provide it to the low-level control mechanism. And finally, the controllers would produce the control input or the torque that is required to perform the tasks. And you can imagine if we have complicated a complicated robotic system, maybe if we have a multi-legged mobile robotic system, then the modeling and prediction and planning can be a complicated task. So in reinforcement learning, this process is done in this way. Let's say we want a robot arm to figure out how to pick up objects. Okay, and the goal here is to develop a system that will use images from the robot's camera. There'll be cameras here, position its gripper correctly and pick up objects. So overall, reinforcement learning utilizes data from experience, and that's why we can see we are moving all these robots to generate as much data as possible. That tells us, so we want to collect data from experience that tells us what are possible outcomes or states that can be achieved by various actions. When the robot picks up an object, like it does here, or fails to pick up an object, we would like to use that experience to improve its actions. And this data, the images that we have collected from these robots will be provided to our reinforcement learning algorithm that would produce a policy that would hopefully perform the task better than the robots did before when they were collecting the data. So as a result, at times, the robot could figure out complex skills, such as if objects are positioned close together, it needs to push them apart and pick up individual objects, as it's doing now. So just because it needs to collect the yellow cube, it pushes the group of objects so that it can try to pick and place the individual objects. So sometimes it misses. So if it tries to pick and misses or drops an object, then it will try again to reposition the gripper and pick. So how does it know that? Because it knew this, it got this experience from the past. So at times, the robot even learns to generalize, to pick unseen object, as we will see here. So it hasn't seen this object before, but given the learning algorithm that we have carried out, it still can pick that object, even though it has a non-uniform weight distribution. So the interesting thing here is that how did the robot know where exactly to pick, given the non-uniform weight distribution of the object? So reinforcement learning, machine learning, you might say it rhymes. So what reinforcement learning has to do with machine learning? In fact, reinforcement learning is one of the categories of machine learning. So machine learning can be categorized into three broad groups of tools. So that is supervised learning, unsupervised learning, and reinforcement learning. So in supervised learning, we would have data with ground truth outputs, which means the data is usually labeled. So we have inputs X and Y, or the target. Therefore, it's called the ground truth outputs. And the goal in supervised learning is to fit a model for prediction, so that in the future, if you have a new set of inputs, the machine learning model will generate an output that is close to the unknown truth output. And usually the data is IID, which means the output does not affect the future inputs in any way. it's independently distributed data. It's independent and identically distributed data. So the output of the model will not affect the input. However, I will skip the unsupervised learning. However, in reinforcement learning, the ground truth is not known, and we only know the rewards. So imagine if we have image produced by our robot as inputs. The images don't have to be labeled. We only know the rewards. And often the data is not IID. What it means is that the output from our reinforcement learning will change the environment such that the future inputs will be different. And here the goal is to find actions that maximizes sum of rewards. So this is the crucial difference between supervised learning and in reinforcement learning. So here are some terminologies, right? If we look at the literatures, we will come across these terms often. So usually reinforcement learning problems will be formulated as a Markov decision process. We have state, we know what is state. It represents the current condition of the environment. We have action. So action will be taken on the environment, and policy is a function that determines the action. So S here refers to state. So for every state, the function pi S will generate an action. So in reinforcement learning, usually we want to find the best policy that we can find such that the sum of rewards can be maximum. And we also have transition probability, reward function, and so on. So if we execute a policy, we would have a path or episode where we begin with state 0. And from state 0, we take action A1. We will, by taking action A1, we will arrive at state S1 as governed by this transition probability, and we will obtain reward 1. And from S1, we take action 2, we get reward 2, we end up in state 2, and so on. So I'll just skip through this. So at the end of the day, the goal of reinforcement learning, if we could formulate mathematically, is to maximize the expectation of sum of rewards over the trajectory distribution or the episode distribution. All right, it's okay. I'll just skip through this. All right. Many of us probably have no access to hardware to collect data and to implement reinforcement learning, probably. So, but no worries. So we can always carry out simulations to learn how reinforcement learning works and how to design the model. And I'm sure many of you have heard or even have used the Jupyter Notebook, right? And it's a web-based interactive development environment for coding and data collection even. It's flexible, where you can configure and arrange the user interface to support a wide range of workflows in data science, scientific computing, and machine learning. However, even though it's convenient, you can share your notebook with others, you can do your coding, you can execute, you can debug, but it makes use of your machine, of your laptop, of your computer, right? So if your computer is slow, it has a low specification, then the whole process will be slow. And as you have guessed, in reinforcement learning, we will do lots of computation over and over again. I kind of skipped this part because I didn't want to burden you with the mathematics. So in reinforcement learning, what we do is that we would compute this quantity iteratively over thousands and thousands of times, and until this quantity converges. and then we will try to discover or come up with a policy through what we call a value iteration scheme. But the point here being is that in reinforcement learning, we have to collect lots and lots of data, and we have to do thousands and thousands of iteration to come up with a solution. And for that, you need good processing power. And probably your Jupyter notebook will not be able to handle that. No worries, we have the Google Collaboratory, or in short, Google Colab. Maybe some of you have heard it, maybe some of you have not heard of this before. So it's just a specialized version of the Jupyter notebook, which runs on the cloud and offers free computing resources. This is the most interesting part, which means if you use Google Colab, you don't need powerful computer, you just need a good internet connection. And the computation will be done in cloud for free. So you can use Google's GPUs and TPUs, tensor processing units, to do your reinforcement learning computations. It provides even more pre-installed machine learning libraries such as Keras, TensorFlow, and PyTorch. And all your Google Colab notebooks are saved under your Google Drive account, just like your Google Docs and Google Sheets files. So therefore, again, you can share with other researchers. You can copy other. You can create a local copy of other notebooks and so on. So let's see briefly the Google Colab. So you can just type. So this is my Google Drive, all right? I hope you can see my desktop here. So this is my Google Drive. So the moment for now, I'll Google Colab. So I'll end up here. Okay. And if I create new notebook, so we have this, right? So this is the name of the notebook. So you can rename this. Let's call this test 1. And this file will appear in my Google Drive. Okay, it will take some time. So as usual, as you use your Jupyter notebook, you can type your code here. And you can execute this code by clicking this button. And you can see Google Colab is allocating some resources for you. It says it's connecting, initializing Python 3 Google Compute Engine backend, and it has RAM 0.75 gig of 12.72 gig and some disk space as well. So it has been executed here. And of course, you can have your text. And so on. All right, so it's very similar to Jupyter Notebook, except that it gives you some computation power. So as you can see, this notebook appears here now in my Google Drive. All right, let's go back to the slides. So how do we simulate reinforcement learning? You know from the previous slides that in reinforcement learning, we have to take actions on our environment. So let's say we have robotic arm. You have to take action. You have to you have to observe the states. You have to collect the reward. And then you have to do this many, many times. You have to collect a lot of data, and then you have to use the algorithm to find the best policy. So recall, policy is a set of actions that you have to take along the way at every state in order to achieve your overall objective. Okay. If you don't have hardware, you need to have a mathematical model representing your system. So we have OpenEye Gym, which is a toolkit for developing and comparing reinforcement learning algorithms. It includes simulated environments ranging from very simple games to complex physics-based engines that we can use to train reinforcement learning algorithms. So basically what it says that in OpenAI Gym, we can make use of the various models of systems in order to implement our reinforcement learning algorithms, again from OpenAI as well. So we have another library called OpenAI Baselines, and it's a set of high quality implementations of reinforcement learning algorithms. So you can get the algorithms, you can implement it and apply it on models again from OpenAI. So let me try to show you what is OpenAI. So I'll close this. So I hope you can see my screen. So if you type gym.openai.com, so this is the website, and you can click on environments. And here we have lots of models that we can use as our system. So for example, we have this classical control, we have this swing up a two-link robot, we have cut pole. Obviously the objective here is to have the pole upright by moving the cut. We have games, Atari games, where you can implement the reinforcement learning algorithm. We have simple robotic systems. So this is the bipedal walker, and we have lunar lander system. We have robotic system. Here, this is called fetch, pick and place version 1. And each of these environments has its own set of objectives, rewards, and observations that you can use to design and implement your reinforcement learning algorithms. Okay. So, for example, if we're talking about the bipedal walker version 2, so here I have Google Colab notebook. Okay, and the way we load this model is by using this command. So gym.make, and we pass in the name of the model. So as you can see here, I pass in bipedal walker dash version 2, which is exactly the same as what is written here. Okay, and of course you need some installation, and so you have to import some dependencies before that. And if you want to find out more about the environment, you can always go to its wiki page. So on the wiki page, you can have more information about the environment. So for example, for this particular environment, the bipedal walker version 2, we have about 24 observations. So the state vector is 24 element long. So we have the hull angular velocity, and so on up to the LiDAR readings. And actions, you have 4 actions that you can carry out. You can have the hip movement, knee 1, knee 2, hip 1, hip 2, 4 actions altogether, and the minimum and maximum values as well. So once again, about the bipedal walker 2 from the gym environment, if you are interested to simulate this, the way it works is that a reward is given for moving forward, total 300 points up to the far end. So that means if it moves to the finish line, the agent can collect up to 300 plus points. If the robot falls, it gets minus 100. Right? This is more like a penalty. So minus reward is a penalty, right? So in applying a motor torque costs a small amount of points. So if you actuate your motor too much, you will lose some points. You will get minus reward. So essentially what you are looking for is for an agent that is optimal. And as we have seen earlier, the state consists these quantities. So if we take random action, I hope you can see this video. If you take random action, this is how the bipedal moves, right? In no particular fashion. And by using reinforcement learning, after 300 episodes, you can see it is crawling already, right? It's moving slightly. It still gets some reward. The reward is minus 100, right? Perhaps minus 100 is better than minus 200. So that's why it came to this state or to this episode. And then if we proceed further with 500 episodes, so we can see it starts to walk in a better way. And then after 600 episodes, it's kind of leaping or jumping forward, and it's moving forward. And if you train higher with more episodes, perhaps you can walk in a regular fashion. And this is the simulation of the fetch, pick and place version 1. So the goal is randomly chosen 3D space. So the goal here is that we have to control the N effector to pick an object and lift to reach a goal. So we cannot see the goal here, maybe we'll see later. So initially, by just executing randomly, this is what we do. It's supposed to pick the black cube and then bring it to the red ball. That's the goal. Okay. And after collecting enough data and executing the reinforcement learning algorithm, we can see it does pick the cube and brings it to the red ball effectively. So note that here we do not do inverse kinematics, we do not do forward kinematics, no trajectory planning. So it learns this purely by doing things randomly, collecting the experience data, and training the reinforcement learning model. So next, this is the humanoid version 2. Similarly, we can get this from the website, from Jim library. So it should be here, all right? So here, I think it's pronounced Mujoko. I'm not sure how it's pronounced, but all these models, they use actual physics engine. So the mathematical model is done according to the laws of physics. And this is a humanoid robot, and the goal here is to make it walk, right? So if we click this, probably we can get, well, nothing much here. We have to go to the wiki page to get more information. So initially, it just does this up to episode 14. We can see that nothing much is going on because the actions are random. It's collecting data, it's improving its experience and its policy. So after episode 5,000, 15,000, 30,000, 60,000, you can see more or less is moving forward. And this is episode 87,000. So it is getting closer to the normal walking gait. So if we were to do this in a conventional controlled pipeline method, we have to design the trajectory, we have to do the inverse kinematics, and then we have to compute the individual trajectory of the joint angles individually. And you can imagine how many joints we have here. In reinforcement learning, this can be done automatically through the reinforcement learning algorithm. So I think I've spoken slightly over 30 minutes. So as a conclusion, I have briefly touched or given the overview of reinforcement learning. And we know that reinforcement learning is a way to make decisions by experience data, all right? And our goal is to come up with a policy such that we can maximize the sum of rewards that we would collect from the beginning till the end. It's not only about the final goal; it's about the journey as well. And we have looked at Google Colab. It's an online browser type environment that you can code, you can execute your Python codes. And the good thing is that you would have free computational resource from Google. That means you can make use of the GPUs, CPUs, and TPUs, tensor processing unit. We have looked at OpenIGym, which is a collection of libraries that provides you with the model of various environments. Okay, and from these environments, you can obtain the observation, you can obtain the reward, you can execute actions in order to design and implement your reinforcement learning algorithm. So we know that reinforcement learning is a learning based on experience. Therefore, data quality is essential. So imagine if you would do simulations, because in simulation you can collect the data fast, right? You can run the simulation fast, maybe 100 times faster than actual hardware. You can collect data, you can design and train your reinforcement learning model. But when you implement the actual hardware, will it work? So that is one of the issues in reinforcement learning, because the data that you obtain to train your model is through simulation, but then when you actually implement it in real hardware, it might not be as desired. So to counter this, of course, you can collect data from the actual hardware itself, right? But as you saw in the earlier videos, you have to collect data from multiple robots at the same time, and that would take forever. I mean, a lot of time, right? And even you have a good quality data, we know that the training time can be very long, because as we saw in some of the simulations, for this one in particular, we had to train this iteratively, and this is up to 87,000 iterations, and still it doesn't perform that good, right? So, and another crucial downside or issues that we have to take into consideration is, again, the exploration versus exploitation trade-off. So we have to make sure the action and the states that we generate from our that is in our data collection, it covers the whole state space. So if we only collect data from a small portion of our state action space, then probably the model will not work correctly when it encounters a state that it has never seen before. So similar to search problems, in reinforcement learning problems, we have this exploration versus exploitation trade-off. So that's all from me. Thank you very much for listening. I would like to maybe apologize if the quality of the audio and video is not the best. So thank you for listening. So now I would like to open for some questions. I don't know how you're going to ask me questions.
Okay, thank you very much. Thank you very much. It's a very interesting talk. Questions are posted on this Facebook okay. Here are some questions. One is from Dr. Ati. Okay. How can we know which system is suitable for reinforcement learning algorithm? Any rule of thumb for using this algorithm?
I'm sorry, Dr. Azlina, your voice is breaking, but I'm trying to go to the
Yes, Facebook page. There's some questions there.
how can we know which system is suitable Oh. So it says, how can we know which system is suitable for reinforcement learning algorithms? Any rule of thumb for using this algorithm? Okay, good question. Sorry, ada gemar ke sekarang?
Oh, this is not okay.
All right. Okay, so that's a good question. We have to make sure our system can be modeled as a Markov decision process. That's the first thing. Which means most important thing is that we have a quantity, an operator, a probabilistic operator that we call transition probability. That means from a state, if I take action A, I can end up in many states with various probability. So, and many problems can be formulated in this way, even our regular control system. So if we could formulate or represent our plan or our system as a Markov decision process, then we can implement reinforcement learning. And remember, reinforcement learning is all about coming up with a policy function where at every state we want to decide, or with this function would determine what is the best action to take in order to maximize the sum of rewards. And the second question, for advancement of new knowledge in reinforcement learning, what will be the trend for research in this area? Okay, wow. So what I've just presented is, so there are many things that are skipped, many technical details that are skipped in this presentation, because or else it'll be too mathematical and no one would appreciate, I guess. So so these days, the direction is moving towards neural networks, deep learning. So they call it deep learning reinforcement learning. So where this policy is not a usual mathematical function or a statement, this will be trained from using a convolutional neural network. You know, so pi is actually a convolutional neural network. So given state, or sometimes given state and action to the convolutional neural network, the output will be the probability of those actions. And various algorithms, there are various algorithms in reinforcement learning and deep reinforcement learning. And some of the algorithms focuses on try to estimate the policy, some tries to estimate or learn the value function, Q value function. These are various, so value function and Q value function are functions of discounted sum of rewards. So if you ask me, so there have been many works on using artificial neural network, in particular deep neural network, in estimating these functions. So that could be, more can be done by using artificial neural network in relation to reinforcement learning. Okay.
I think there's another question, Dr. Kumar.
Yes, so this is from Dr. Hazlina yourself. So I think it says reinforcement learning looks very promising, but why is it not as popular as other AI algorithms? What about those walking robots by, for example, Boston Dynamics? Do they use reinforcement learning to train the robots how to walk? They do. Many robots, especially in the US, they have implemented reinforcement learning. So why is not very popular? Why is not super popular? It is popular. Why it is popular? Because the behavior that the robot will exhibit after we have successfully applied reinforcement learning can be very interesting. But one of the drawbacks or one of the issues with reinforcement learning is that we have to collect data, right? So imagine if you have cheetah robot, right? So you execute some actions, and then it does produce new states and rewards and so on. But then you have to reset the robot to its original state. So how you want to do that, right? So you have to carry the robot and then reset the legs to the original state, and then apply another set of actions, and that can take time and effort. So I would say that those are the challenges that hampers the application of reinforcement learning. In simulation, we can reset it by program, but in actual hardware, how can we reset a robot to the original state so that we can apply different action? So that is a bit tricky. Okay, Dr. Hazlina.
Thank you very much, Dr. Kumar. I think that is a very enlightening and very exciting thought. All right, so we don't have any more question at the moment, but I really enjoy what you have shared with us. I'm sure the other audience are enjoying it as well. I would like to thank you on behalf of Malaysian Society for Automatic Control Engineers, MOSTI, as well as ASEAN Committee on Science, Technology and Innovation. And I hope that in the future, you will be able to share more talks organized by us, inshallah. Thank you very much, Dr. Kumar. And thanks everyone for joining this session. So hopefully we'll see you next week. Happy New Year. Bye-bye.